There's something that is called the remainder estimation theorem. And you can use the integral test to come up with this remainder estimation theorem, but it basically goes something like this. If you have the sum, or the sum as n goes from 1 to infinity of an, you can write this as the sum as I goes from 1 to n of ai plus some other terms, and these other terms is basically called the remainder. So if you call this the sum and this the partial sums, then we have s minus sn equals to rn if you subtract sn from both sides. This is called the remainder theorem. This is called the remainder, and then the remainder estimation theorem says that the sum of a series is actually the remainder of the series. Let's see if I have it correctly. Yeah. This remainder, so they use like upper sums and lower sums and whatnot, and basically it goes like this. The remainder terms on a series is bounded by the integral from n plus 1 to infinity of f of x dx, and the integral from of f of x dx as n goes from x goes from n to infinity. So with that, you get s minus sn between the integral from n plus 1 to infinity of f of x dx, because this is the same as s minus sn, the integral from n to infinity of f of x dx, and then if you add sn to both sides, you get sn plus the integral from n plus 1 to infinity of f of x dx less than or equals to s sn plus the integral from n to infinity of f of x dx. So this says that the sum of a series is between Sn plus the integral from n to 1 to infinity, and Sn plus the integral from n to infinity. So remember, let's say we want to estimate the sum as n goes from 1 to infinity of 1 over n squared. Remember that the answer for this, which we're going to call s, is pi squared divided by 6, okay? So, but suppose that we didn't know what it was. We still can estimate. So let's say we want to estimate that with n equals to 10. So using the inequalities that I just described, so remember it was Sn plus the integral from n plus 1 to infinity f of x, and s, and then Sn plus the integral from n to infinity f of x dx, like this. So with n equals to 10, you got S10 plus the integral from 11 to infinity of 1 over x squared, because this is the function corresponding to 1 over n squared. So S will be between that and S10 plus the integral from n to infinity of 1 over x squared dx. Now, the integral from n to infinity of 1 over x squared is the limit as b approaches infinity of the integral from n to b of x to the minus 2 dx. And this is equals to the limit as b approaches infinity of minus 1 over x from n to b. So plugging in the b and the n, we get the limit as b approaches infinity of minus 1 over b plus 1 over n. And because we're taking the limit as b approaches infinity, n is constant, so we get the 1 over n. In other words, the integral from n to infinity of 1 over x squared dx is equals to 1 over n. Therefore, this integral right here, the integral from 11, so this means that the integral from 11 to infinity of 1 over x squared is equals to 1 over 11. And the integral from 10 to infinity of 1 over x squared dx is 1 over 10. So in other words, this guy right here, which I'm going to put in the other page because it doesn't fit here, is S10 plus 1 over 11 less than or equals to S, and S10, plus 1 over 10. And what is S10? Well, S10 is just 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus blah 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 all the way to 1 over 10 squared, because it's just from the partial sums with n equals 10. And this is equals to 1.54977. 1.54977. So therefore we have 1.54977 plus 1 over 11 is less than or equals to S, and then 1.54977 plus 1 over 10. Take this and add them up, so you get 1.64068 is between that and 1.54977. And if you take the midpoint of this interval, then S will be approximately equals to. So it's between those two numbers. It's within that interval, so S is approximately. You can take the midpoint of that interval, so 1.64068 plus 1.64977 divided by 2, or S is approximately equals to 1.64, and I don't remember what the other numbers are. But anyway, so this is what S is. And remember that the sum, the exact sum, is pi squared over 6, which is 1.6449 and blah blah blah. So this is an approximation to the exact sum. So even though we didn't, we know this from advanced calculus, but in calculus 2 we're not supposed to know it, but at least we can approximate it, and this is just a way to check. Alright, now suppose that they want to know how many terms are required to approximate the sum as n goes from 1 to infinity 1 over n cubed with n 0.01, so with an error of 0.001. So in other words, you want to find n such that s minus sn is less than 0.01, but s minus sn, that's Rn, less than 0.01. But Rn, remember that s minus sn, it was s minus sn was between this integral from n plus 1 to infinity f of x dx, and then the integral from n to infinity f of x dx. So if I can find n, the integral of 1 over x cubed dx, and if I want that to be, if I can bound that by 0.01, then Rn will be bounded by that, because this is bigger than Rn. Like that. So just like we did before, the integral from n to infinity of 1 over x cubed dx is equals to the limit as b approaches infinity of the integral from n to b of x to the minus 3 dx, and this is the limit as b approaches infinity of minus 1 over 2x squared. So from from n to b, this is equals to the limit as b approaches infinity of minus 1 over 2b squared plus 1 over 2n squared. So this is 1 over 2n squared. So basically you want 1 over 2n squared to be less than 0.01, and then you just solve for n. So I'll just do it like right here. 1 is less than 0.01 times 2n squared, so 0.02 n squared is bigger than 1, and n squared is bigger than 1 over 0.02, and n is bigger than the square root of 50, like this. So n is bigger than 7.07, so you take n to be bigger than or equals to 8, because n has to be an integer. So it takes approximately 8 terms in order to approximate this sum to within an error of 0.001. In other words, I'll put it right here as 8. It'll be 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus blah 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 plus 1 over 8 cubed. And this number right here that we get I don't remember how, what was it, maybe like 1.19 or something like that, 1.19. So this is an approximation to within 10 to the minus 2. Okay, we're gonna call this the integral remainder theorem, or integral estimation theorem. Thank you.